The Mittag-Leffler function is a natural generalization of exponential functions. Its simplest form was introduced in 1903 by the Swedish mathematician Magnus Gustav Mittag-Leffler. The function is also referred to as the one-parameter Mittag-Leffler function. It was later generalized to accommodate two or more parameters. In fractional calculus, Mittag-Leffler functions play a role as fundamental as exponential functions in integer order systems. This video provides an overview of the definitions and computational methods for various types of Mittag-Leffler functions. First, we write the Taylor series expansion of the exponential function. Since the gamma function is the natural extension of factorial function, we can replace k factorial with gamma of k plus 1. In other words, exponential function e to the power of z is a special case of one-parameter Mittag-Leffler function e alpha z. That is, e1z is equal to e to the power of z. Here I have shown the curve of one-parameter Mittag-Leffler function for various values of alpha. Consider again the definition of one-parameter Mittag-Leffler function. If 1 in the gamma function is replaced by a variable beta, two-parameter Mittag-Leffler function can be introduced. If beta is equal to 1, the two-parameter Mittag-Leffler function can be reduced to the one-parameter Mittag-Leffler function. Here I have stated the definition of the two-parameter Mittag-Leffler function, in addition the series convergence criteria. We can even define a 3 or 4-parameter Mittag-Leffler function. Mathematicians often take generalization to the extreme. Here we see another symbol introduced. It is called Pochhammer symbol, but what is the definition of this symbol? Pochhammer symbol is also known as the rising factorial. In the Pochhammer symbol, if gamma is equal to 1, then we get k factorial. When it comes to generalization, mathematicians take it even further. Here is the definition of the multi-parameter Mittag-Leffler function. It is amazing that we reach this from a simple exponential function. Derivatives of integer order for Mittag-Leffler functions are often encountered in fractional calculus. There are many properties in the derivatives. Here I have stated an informal proof of n-order derivative of the two-parameter Mittag-Leffler function. The reason I say informal is because the formal proof needs a straightforward induction. So we reach the result as stated in the theorem for the n-order derivative of the two-parameter Mittag-Leffler function. Well, what about the numerical evaluation of Mittag-Leffler functions? Well, there are many papers published for the efficient computation of Mittag-Leffler functions. But before talking about papers, you should know that if you have watched till now, your attention span is much higher than majority of people out there and you are really passionate about mathematics. One method is quadrature approximation of contour integral representations. This method involves computing the Mittag-Leffler function via a quadrature approximation of a contour integral representation. Comparisons between parabolic and hyperbolic contours have been made with special attention to evaluation on the real line. Handling poles in the integrand is a key aspect of this approach. One of the key references is Diethelm, 2005, which introduces a collection of numerical algorithms for fractional models. The paper includes a dedicated section on the Mittag-Leffler function and also outlines a method for computing its derivative.